In the previous video, we discussed the idea that if we insert a dielectric in between the capacitor plates, what will happen is the dielectric will improve the permittivity in between the capacitor plates. Okay, that space in between the capacitor plates, the permittivity will be improved due to the presence of this dielectric. Okay, so if we improve the permittivity of that space in between the capacitor plates, it will cause the capacitance to increase. Okay, so the dielectric always increase the capacitance of a capacitor. So if you insert dielectric, the capacitance will increase. So we can represent it by this equation over here. C naught with a naught at the bottom, what it means is that it is the capacitance before we insert the dielectric. Whereas if there's no naught below, what does it mean? That is the capacitance after we insert the dielectric. So this is before insertion of dielectric, this is after insertion of dielectric. And as we mentioned just now, insertion of dielectric always causes the capacitance to increase. Therefore, we know that after insertion, C will definitely be larger than before insertion, C naught. C is always larger than C naught. Because we know that C is always larger than C naught, therefore we know that this factor over here, which we call as dielectric constant or relative permittivity, this value here must always be larger than 1. Okay, this value here, dielectric constant, it is sort of like a number that tells us how many times does the permittivity improve by, or how many times does the capacitance improve by. So let's say this epsilon r, this relative permittivity, this dielectric constant, let's say this value is equal to 2, let's say. Then what does it mean is that the permittivity improved by twice the amount of the permittivity before insertion of dielectric. Okay, so it means by if you insert the dielectric, the permittivity will improve by 2 times. That is what it means if our dielectric constant is equal to 2. Okay, so if we improve the permittivity by 2 times, then the capacitance will also get improved by 2 times. So our capacitance after insertion of dielectric will be twice the original amount, which is before the insertion of dielectric. Okay, so that's the idea that we talked about in the previous video. Then in the previous video, we also mentioned that the definition of capacitance, the value capacitance here, it is the ratio of the charge stored in between the charge stored in the capacitor to the potential difference between the capacitor plates. So it's a ratio of Q to V. So we know that if we happens to increase the capacitance by inserting a dielectric in between it, the increase in capacitance must also affect either Q or it will affect either V. Okay, either Q or V will be affected due to the increase in capacitance when we insert a dielectric. Okay, so the idea is, will it be the Q that increase along with C when C increases, or will it be V that decrease when C increase due to the insertion of dielectric? That's the topic of what we want to discuss in this video over here. Okay, so here you can see that on my left, we have a capacitor which has not been inserted with dielectric yet. It is empty right now. Okay, you can think of it in between the plates, it's vacuum. So right now, the C, the capacitance, we call it as C naught, and it's equals to Q naught and V naught. Okay, so I write it as Q and V naught. Q naught represent the charge stored before you insert the dielectric. So before there's any dielectric, this is a charge stored in the capacitor. Before there's any dielectric inside the capacitor, this is the potential difference between the capacitor plates. Okay, so now you insert the dielectric, it will cause the capacitance increase. Therefore, this C value over here, this new capacitance here, will definitely be larger than the old capacitance, which is before insertion of dielectric. So C will be larger than C naught. But we know that this C is still tied to its definition, which is the charge stored after insertion divided by the potential difference after insertion. Okay, so what we know right now is, because of this equation, C naught multiplied by the relative permittivity will cause us to have an increased capacitance. This is what we know from earlier. So definitely we will know that C naught will be less than C. Okay, because the C increases, the capacitance increases. But if you relate it to these two equations over here, now you have things to think about. This increase in capacitance here, does it make your does it change the Q or does it change the V? Okay, that is what we can think, because we know that C changes. If C changes, it's either Q that needs to follow and change, or it's V that needs to follow and change. So if it's Q, let's say if it's V that follow to change, what will happen is we need our new V to be less than the OV. We need to make this value smaller so that the C can be a larger value. Okay, so this is one possibility at V where the new potential difference will be less than the old potential difference. Or in other words, insertion of dielectric causes the potential energy to decrease. Okay, maybe I should flip everything, write the new on the right hand side. So initially it's larger, after it's smaller. So this one is assuming that the Q is constant. Okay, so this is one possibility. The Q doesn't make any changes. It is the V that follows along the increase in C by decreasing the V. Okay, V changes but Q remain constant. Okay, based on this equation. Another possibility that of what might happen is the V won't make any changes. The V is kept constant. But what happened is the Q will experience changes from Q0 to Q. So it means when you insert the dielectric, your Q will follow along the change of C and causes change of Q. So we know that if you want to increase C, we have to increase the numerator. So that means the Q, the new Q, will have to be larger than the old Q. So Q0 will be smaller, Q will be larger. So this is Q increases. If we increase the capacitance, the charge will follow along and increase as well. Okay, so in this case, what is constant? V is constant. Okay, so here are two possibilities of what might happen if we increase the capacitance by inserting the dielectric. So whether it is this first situation that is true or it's the second situation that is true, it's actually a case-by-case thing, where different case you encounter scenario 1 where the voltage changes but the Q remain constant. Certain scenario you encounter this second scenario where the charge changes but the potential difference remain constant. Okay, so this is what we want to study for today. Okay, we know for now that the insertion of dielectric must increase the capacitance of capacitor. So the capacitance must increase. So it goes from C0, which is initially a smaller value, to C, which is a larger value. Okay, so the change from C0, which is a smaller value, to C, which is a larger value, will causes two possible scenarios. Scenario 1 is it will not affect Q at all. So the Q going from initial Q0 to final Q, before dielectric there's Q, after insertion of dielectric there's Q, but the two Q are still the same. There's no changes in the charge stored in the capacitor even when we insert dielectric. The charge stored remain the same. Okay, but if we kept Q constant, what must change will be the potential difference. So if Q is constant, then the potential difference must change. Change in what way? We want to make the capacitance larger, so we have to make the denominator to be smaller. So in that case, we can see that the potential difference actually decreases. Okay, so the increase in capacitance causes the potential difference across the capacitor to decrease. That's scenario 1, possibility number 1. What might happen? Case 1, okay, where the Q remain unchanged. Scenario 2 is the opposite of it. Scenario 2 is you still have your capacitance increase because dielectric always increase the capacitance. So this one is a must. Our capacitance must increase. But instead of Q being kept constant like scenario 1, for scenario 2, it is V that is being kept constant. So the V doesn't follow along the change of C. The V will still remain the same. So that means by even if you insert the dielectric in between the capacitor plates, the potential difference between the capacitor plates remains the same. The V never changes even after we insert the dielectric. But we know that equation must still make sense. So if we don't change V, then Q will have to be the one that changes. So if you want to increase the C, that means your numerator must increase, follow along and increase as well. So you see that the charge stored in the capacitor will increase when we insert a dielectric in between the capacitor plates. Okay, so scenario 2, you'll see an increase in Q. So the increase in capacitance causes the amount of charge stored in the capacitor to increase. So this is possibility number 2. And possibility number 2 again makes the potential difference to be remain unchanged. Okay, so now we'll try to discuss under what situation will you encounter scenario 1, under what situation you will encounter scenario 2. Okay, scenario 1 will happen under a specific condition, scenario 2 will happen only under a specific condition as well. So let's discuss the scenario. Okay, so both scenarios can happen but under different conditions. So let's study the first scenario. Okay, so the condition 1 where is when we insert the dielectric into a fully charged capacitor which is not connected to anything. Okay, so we have a capacitor that we already connect to battery, we let it fully charge, then we remove the battery from the capacitor. So right now we have a fully charged capacitor, you have a positive plate and a negative plate, and it's fully charged, but it's no longer connected to anything. Okay, if it's no longer connected to anything, we try to think about it. Is there any possibility for the charge to move? Well, if you want your charge to move, you have to provide a path for the charge to flow. So in this case, if we do not connect the capacitor to anything, you can say if we do not connect it to anything, then basically there is no path. Okay, we don't have any path for our charges to flow. Okay, there's no way for our charges to go back from the positive plate, go back to the negative plate. It just cannot be done because there is no path available for it to move from the positive plate back to the negative plate. So because of that, we already removed the possibility for the charge stored in the capacitor to change. The charge stored in the capacitor must remain unchanged because we cannot let the charge to flow out, we cannot let the charge flow in anymore. So the Q must remain constant in this case. So that's the condition if we do not connect anything to the capacitor, or we say we isolate the capacitor. Isolate means by lonely, right? So we isolate, not connect to anything. Okay, so if you isolate the capacitor, what happens is there's no path available between the two plates. Like what I said earlier, you don't have any path to flow, so your charges, you cannot flow. Charges cannot move from the positive plate back to the negative plate. You cannot reduce the charge stored in the capacitor. You cannot increase the charge stored in the capacitor. There's nothing you can do to the charge. It is stuck there. There's no path to move. So in that case, Q must be constant in this case. So if Q is the one that is constant, and we know that insertion of dielectric causes increase in C, so that will be C, that will be, initially you have C naught is equals to Q naught over V, but now because of your insertion of dielectric, you know that your capacitance increase, capacitance gets to a larger value, but you know that your charge stored cannot make any changes. Your charge stored cannot make any changes. Why? Because your capacitor is not connected to anything, so it cannot flow out. The charge cannot flow out, the charge cannot flow in. So the charge stored initial and final must be the same. Okay, you cannot make any changes to the charge stored in the capacitor because there's no path to flow. So if your Q remain the same, then the only way to make this equation make sense is by decreasing the potential difference between the plates. So you make the potential difference to become smaller in order to increase the capacitance when you insert the dielectric. So what's the effect of Q constant, C increases? It will cause the potential difference between the plate to decrease. Okay, so potential difference between the plate decrease comes back to what we say earlier. This will be scenario 1. So scenario 1 happens under the condition. What kind of condition? Our capacitor is isolated. If our capacitor is isolated, scenario 1 will happen. Okay, let's continue to condition number 2. Condition number 2 is if you insert the dielectric into a fully charged capacitor while the capacitor is connected to a battery. Okay, so condition 1 just now, there's no connection to anything. We call it as isolated. But now condition 2, we are going to insert the dielectric while the capacitor is still connected to the battery. Okay, so the capacitor is still connected to battery. So what do we know? If it's still connected to the battery, then when it's fully charged, the voltage or the potential difference across the capacitor must be equal to the potential difference across the power supply. This must be true when we fully charge a capacitor. Okay, when you fully charge a capacitor, V of the power supply will be equal to the V of the capacitor. So the V capacitor is equal to V battery when it's fully charged. So that means by as long as the battery is there, as long as we are connected to the battery, at the end of any charging process, it will still go back to the same potential difference, which is the potential difference of the battery. You cannot go larger than the potential difference of the battery. You cannot go less than the potential difference of the battery when you fully charge the capacitor, because you have to charge it. You charge using the power supply, right? So the power supply provide how much energy, that's how much energy you are going to get. Okay, so the V battery does not change because we are connecting it to that same battery along the way. So that means by the V capacitor must be constant. When you fully charge it, you will have to go back to the same value, which is the potential difference across the battery. So that V must be constant. So if V constant, C increases. Well, let's go through the same process again. Initially, you have your C naught is equals to Q naught over V naught. If you insert your dielectric, what happens is your capacitance will increase, but because you know that you connect it to the battery, so that means that when it's fully charged, you have to go to the same potential difference, which is the potential difference of the battery itself. Okay, so let me write V naught will be equals to V, and it will be equals to the V of the battery. That is what happened when it's fully charged. Okay, so if your V naught and your V are the same, so to make our capacitance increase, it must correspond to an increase in the amount of charge stored in the capacitor. So that's why you see Q will increase. Okay, so therefore come back to what we discussed earlier. If you want to have scenario 2 where the V remain unchanged and the increase in C causes an increase in Q, if you want to have this scenario, what do? You have to make sure V remain unchanged by connecting the capacitor to the power supply while inserting the dielectric. Okay, you have to insert dielectric while it is connected to the power supply. Then the V will not change. If the V will not change, then it has to be the Q that changes. Okay, so to wrap it up, scenario 1 where Q remain unchanged, V decreases, only happens if the capacitor, we insert the dielectric when the capacitor is not connected to anything. Okay, scenario 1 happens when it's isolated. If you are not connecting the capacitor to anything and you insert the dielectric, the charge will not change. What has changed will be the potential energy, the potential difference to decrease. Okay. If it's scenario 2 can only happen if you connect the capacitor to a power supply connected to battery. If you connect it to the battery, then the potential difference across the capacitor when it's fully charged will still remain the same. So V remain the same. If C increase, what must change will be the charge stored in the capacitor. So the charge stored in the capacitor Q must increase as well. Okay, so these are the two different scenarios that we might encounter when we insert a dielectric into a capacitor. So by looking at the condition, whether it's connected to anything or whether it's connected to battery, we can deduce whether it's the Q that should be changed or it's the V that should be changed. And this concept will be further reinforced through a few examples that you can see in the other videos.